This video pertains to trig integrals, the blue boxes, and the tables. You have the formula sheet that you need to work any problem in the section pertaining to trig integrals. You have your tables for the products of sine and cosine, and also for the products of tangent and secant. On the second page, you have several blue box formulas for sine squared and sine cubed, cosine to the fourth. Later on in the section on trig integrals, you have the blue boxes or the formulas for tangent squared and tangent cubed and secant cubed. These are a few of the trig integrals that are not already on the formula sheet. You need to write these two in. The antiderivative of cotangent x is easily found by rewriting that as cosine of x divided by sine of x, and performing u substitution. Eventually, you will see that you receive the natural log absolute value of sine x plus c. The antiderivative for cosecant of x with respect to x is negative natural log absolute value of cosecant x plus cotangent x plus c. I will not ask you to derive the formulas, but I will ask you to use the formulas on possible tests and quizzes. So these are also famous blue box formulas. Again, I call them blue box formulas because the old version of the textbook, Anton and Bevins, actually highlighted the formulas in the color blue. And you do not necessarily see the color blue in your current Pearson edition of the textbook. So I have a few examples that I'd like to go over in addition to class lecture. Before I show you additional examples, I wanted to remind you about the breakdown of the section. Roman numeral number 1 would be powers of sine and cosine, and they gave us reduction formulas, if you remember, where n had to be a positive integer greater than or equal to 2. In class, I was able to prove just a few of the blue box formulas for sine of x to the power of n and cosine x to the power of n. After showing you and proving to you a few of those, I said to just now refer to the formula sheet, and if you ever have to integrate powers of sine and cosine, namely sine squared, cosine squared, sine cubed, cosine cubed, sine to the fourth, cosine to the fourth, that you should just refer to the blue box formulas or the formula sheet, which these were derived from the reduction formulas. So no longer go through the reduction formula, but go straight to the blue box special or blue box formula. That is a famous trig integral formula. The next Roman numeral involved a table, products of sine and cosine, in standard form, and this is an x. Sine x to the power of m times cosine x to the power of n with respect to x. You need to be able to see if m is even or odd, n is even or odd. Both m and n need to be positive integers, and again, it needs to be in standard form. If you have it in standard form, you can decide which particular section to follow. N is odd, m is odd, and both are even. We worked one or two examples in class, and I'm going to show you another one in this video. But basically, follow the bullets and follow the necessary identities and substitutions, and it will lead you to the correct answer every single time. But again, make sure you're in standard form. There are other products of sine and cosine that don't involve exponents, but involve these integrands: sine of mx times cosine nx, sine of mx times sine of nx, cosine of mx times cosine of nx, and the way to solve those would be to rewrite these integrands using famous trig identities. Now, the trig identities are given on your formula sheet, the three that you see here on the second page. And you can see alpha and beta represent mx and nx. Again, we worked an example of one of these in class, and you will need to have it in standard form. I took the liberty of rewriting the trig integrals. Again, alpha is mx and beta is nx, so that you know how to plug it into the identity. Roman numeral number 3 would be powers of tangent and secant. So tangent x to the power of n, secant x to the power of n. N is a positive integer greater than or equal to 2. Again, these are two very special integrals that are famous blue box formulas on your formula sheet, but they don't necessarily apply here to the reduction formulas because n needs to be greater than or equal to 2. On your formula sheet, you have tangent of x to the power of n and secant of x to the power of n reduction formulas. And they give us famous blue box specials or formulas for tangent of x, secant of x. Notice that n is equal to 1. So the section gives you alternative methods to coming up with the formulas for each of these. But the textbook does use the reduction formulas to prove the blue box specials for tangent squared, tangent cubed, and secant cubed. So from now on, if I give you an integral that involves tangent or tangent squared or tangent cubed, you'll no longer have to go through the methods that they use to prove the blue box specials. You can just go straight to the blue boxes, and I'll show you an example of that. Again, make sure that you're adding the antiderivative cotangent is natural log absolute value of sine x, and the antiderivative cosecant x is negative natural log absolute value of cosecant x plus cotangent x, and both of those include a plus c because they're indefinite integrals. The next Roman numeral, and before I go on to Roman numeral number 4, I actually have the proof for the antiderivative of tangent x. I've given that to you in class. You would change that to sine of x over cosine of x, and you would do u sub. You would let u be the denominator cosine x. Through complete u substitution, you'll be able to prove that that's the natural log absolute value of secant x plus c. For the derivative or antiderivative formula for secant x, this is what they do in the textbook. They multiply by a form of 1, secant of x plus tangent x over secant x plus tangent x. They multiply numerators together and get secant squared x plus secant x tangent x, and they multiply denominators. Well, this is understood 1 times secant x plus tangent x is my denominator. Then u sub is the entire denominator of secant x plus tangent x. Its derivative is the derivative of secant is secant x tangent x, and the derivative of tangent is secant squared x. That just so happens to be your entire numerator. Therefore, this becomes the antiderivative of 1 over u du. Very easily. Your denominator is u, and your du is your entire numerator. You already have it in there. Therefore, that's the natural log absolute value of u, which is the natural log absolute value of secant x plus tangent x plus c. So there you have the proof of one of the famous blue boxes, secant of x. And again, to do the tangent of x, all you've got to do is rewrite it as sine over cosine, and let u be cosine x, and then go through u sub and eventually prove that it's natural log absolute value of secant x. Some textbooks also write that particular formula, and I can show you here on the formula sheet if I can find it. I'll do that here. Some textbooks, so I'll do this very quickly in case you forgot in class. The way to derive the blue box special is to rewrite it as sine over cosine. Let u be cosine x, and you have to know the derivative of cosine is going to be a negative sine x. So I would need a negative on the inside and the outside. And then changing over 1 over u du. And that's going to be negative natural log absolute value of u plus c. So some textbooks will allow you to leave it as negative natural log cosine of x plus c. And then other textbooks, they want you to go a step further, and that's how they come up with the blue box formula. That's the natural log absolute value of cosine x to the negative 1 power. The only thing that's raised to the negative 1 power is the absolute value of cosine x. And that's by property of logarithms. So that's natural log of 1 divided by, essentially you could say cosine of x. And 1 divided by cosine is secant. Therefore, you get the absolute value of secant x. And there's the blue box formula that you have on your formula sheet, which is here. But do keep in mind, some textbooks say that you could use this one or this one. I would say that the natural log absolute value of secant x plus c is more condensed than this one, since we can apply a logarithm, a property, and we can use this negative 1 as an exponent and make that 1 over cosine, which is secant. And so I like both. I think that sometimes it will depend upon the actual application problem that you may be working. Sometimes this is the better form with a certain application problem. Sometimes this is the better form with a certain application problem. I don't have examples of application problems to show you where they prefer this one over this one, but I am certain that there are application problems where this would work best, and then other problems where this particular formula would work best. And the only thing you have to worry about now is not how to derive it, but how to use it. I think I told you this in class. I could give you this as an example. I'm not going to work this example, but I could ask you to find the antiderivative of tangent 5x. Remember, the overall plan is to do u sub correctly, and then match it up with a blue box formula. And then last step, always go back to x in your final answer if it's an indefinite integral like this one. So u sub first. After you change over to u sub, and again, you'd have to put a 5 on the inside and a 1/5 on the outside. Now you go to your blue box special and remind yourself that the antiderivative of tangent x or tangent u is natural log absolute value of secant u plus c. And I would need to use u since I am in u at this point in time. But eventually, after distributing the 1/5, you will go back to x by remembering that u is 5x. And that's the general process of any of the test questions. Now, the fourth Roman numeral. Oh, got a little bit ahead of myself again. I have the proof for tangent squared. Now, the textbook goes through the reduction formula for tangent squared, which is here, and they let n equals 2. But there's an alternative way to prove the blue box special for tangent squared. You will not have to prove it. I just think it's kind of neat to know how they prove it. So they use the reduction formula or they use the alternative method. In place of tangent squared, they use the identity that tangent squared is equivalent to secant squared x minus 1. And we know that from Calculus 1 that that's a Pythagorean identity. Remember, we know that sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 equals secant squared theta. And there's another one, cotangent squared theta plus 1 equals, and I'll let you fill that one in. But if you use the one in the middle here, tangent square theta or tangent square x is secant square x minus 1. Well, then I broke this up into two indefinite integrals, one with secant squared and one with the number 1. We memorized in Calculus 1 that the antiderivative of secant squared is tangent x, and the antiderivative of a negative 1 is a negative x. So there's the blue box special without having to ever use the reduction formula, letting n equal 2. It may be just as easy to plug in n equals 2 here and use this to find the antiderivative for tangent squared x. But I do know that this is a nice, easy alternative. The fourth Roman numeral would be products of tangent and secant. That involves tangent x to the power of m and secant x to the power of n. And you'll go to this table. Again, make sure it's in standard form where tangent is first and then secant. You'll want to know if your m is even or odd, your n is even or odd, because you have the cases where n is even, m is odd, m is even, and n is odd. The bullets tell you what to do, and then you have your identities. And again, we did do one in class, but I feel like I have another example in the handout here. Alternative methods would be Roman numeral number 5. And the reason for this particular section is it can help you to avoid Roman numerals 1, 2, 3, and 4 if easier and it's possible. Therefore, I may have misspoken earlier. I think I have examples for you now of everything but this particular type product of sine and cosine, sine of mx, cosine of nx. I do have an example of a power of sine or a power of cosine. I have an example here of products of sine and cosine using the table, but not an example of this. I do have an example of powers of tangent and powers of secant. And I also have an example of products of tangent and secant. And then the last problem I have is an alternative method example. So let's get started. What I did is I created a couple of problems in Pearson's My Math Lab or test generator. And I basically came up with 3 of those multiple choice, and I know the answers, and I worked them all out so that I can show you here today in the video. One other thing I want to mention is these 2 are on your formula sheet, and these 2 are not already on your formula sheet. I hope to type these in somehow or some way, write those in so that I can attach those to your test. I may have time just to do this and not have time to actually type those in, but I need to add those to your formula sheet. And you may need to go ahead and add those to your formula sheet also to be able to do some of my Math Lab homeworks and some of the Blackboard homeworks. So this is what I entitled the examples. Lecture video for Test 4, Chapter 8, Fall 2017. I said that I cover integration by parts, but I actually started with trig integrals. I hope to make other videos pertaining to trig substitution and partial fraction decomposition. But this first video is going to concentrate mainly on trig integrals. I may add to this list of problems later because it was intended to be a video or a practice set for the entire chapter, including integration by parts. But for now, I'm starting with trig integrals. I feel like I covered integration by parts in class very heavily, and I gave gave you many, many examples from old quizzes and old tests and things like that. But I feel like the section on trig integrals has so much in it that I wanted to give you some more examples. So the following 3 problems are problems that I'd like to do now. And all of these come from the section on trig integrals. This one is a power of cosine. This is a product of sine and cosine used in the table. And this is a power of secant. So I am going to show you how to receive the answers. Let you take a moment maybe to write down problem number 1, 2 times the cosine of 5x to the power of 4. And then you have your answer options there. So problem number 1 is first. I wrote that down on separate paper, and I wrote it down this way. I went ahead and did my u sub because I knew that there was a blue box special for cosine of u to the 4th power. U is 5x and du is 5dx. This 2 really has nothing to do with the u sub, so I just moved it outside of the integral. So there's my next step. And then I know that I need a 5 on the inside and a 1/5 on the outside. So this is still before I change over to u. This allows me to go to 2/5 antiderivative of cosine u to the 4th power, and now I'm ready for my blue box. In or on your formula sheet, you will see that your blue box special, and if I ask you for this formula, you cut it and paste it to your work in the box, and you use x, exactly what you see from the formula sheet. But in showing your work, you need to replace x with u. So consider this to be the cosine of u to the 4th power du. So it's going to be 3/8 u plus 1/4 sine of 2u plus 1/32 sine of 4u plus c. And that is exactly what you see here. There you go. So 3/8 u plus 1/4 sine of 2u plus 1/32 sine of 4u. And all of that has been multiplied by 2/5. Before I go back in and substitute in for u, I do distribute the 2/5 to every single one of those fractions. The first one is going to be 6 over 40, and then 2 over 20, and then 2 over 160. And they reduce down. So I still have not gone back in and substituted in for u because u is 5x. 6 over 40 reduces to 3 over 20, 2 over 20 reduces to 1 over 10, and 2 over 160 reduces to 1 over 80. And then now I go back and substitute in for u. U is 5x. 2 times 5x, 4 times 5x. Now the 5 and the 3 over 20 will reduce one more time to 3/4 x, and here's your final answer. Plus 1/10 sine of 10x plus 1 over 80 sine of 20x plus c. As you can see, it's not that bad once you do your u sub, and then you find the blue box special, so you can integrate and then go back to x and simplify and reduce anything that you possibly can down, reduce it down in your final answer. So that is answer number 1. And according to the handout, that is going to be letter D. So 3/4 x plus 1/10 sine of 10x plus 1 over 80 sine of 20x plus c. Answer is D. You can pause this video, you can print this page, but the answer to this one is D. Okay, next question. And I'll give you a moment to copy that down or to let that sink in. This is cosine of 6x to the 2nd power times sine of 6x to the 3rd power, but this is a definite integral, so I'm going to get a final numerical answer here for this one. And again, I have the work for this. I'm going to show you what this looks like. the first thing I did is I noticed that it wasn't in standard form. So I rewrote it in standard form. Sine cubed times cosine squared. So m is 3 and it's odd, and n is 2 and it's even. I go to my table and I pick out the fact that, now that it's in standard form, I have, again, going back, m is 3 and it's odd, n is 2 and it's even. So I am actually going to have to go with this one. M is 3, and remember it was sine cubed times cosine squared. N is 2, and it's even. So the only one that makes sense is this one where m is odd, because m was 3, n was 2 in standard form. I'm going to split off a factor of sine. I'm going to apply the relevant Pythagorean identity, and I'm going to let my u sub be u equal cosine of x, just like they tell me here. So what you can see is that my method is to go through one round of u substitution. And I want to write something down for you. Some people with this particular problem, and let me go back to this step in standard form, they'll do 2 rounds of u sub, and there's absolutely nothing wrong with doing 2 rounds of u sub. If you do 2 rounds of u sub, u is equal to 6x and du equals 6 dx. So you would need a 6 on the inside, and you would need a 1 over 6 on the outside. Since we're still in x at this point, I'm going to leave my original limit 0 to pi over 2. Oh, I forgot my 6. And then you would change over, whoop, I better not do that, to u. So that's going to be the sine of u cubed times the cosine of u squared du. You would need new limits. Here x was 0, so u is going to be 6 times 0, which is 0. X was pi over 2, so u is equal to 6 times pi over 2, which is 3 pi. So now we're going to go from 0 to 3 pi that were in u. Now that is u sub once. Oh, excuse me, this is going to be u sub twice. So that's the first time I've gone through u sub. Then I'm ready to go to my table, and they say to break off a factor of sine. So that is going to look like this. That's sine squared u, cosine squared u, sine u. So I haven't changed the problem by breaking off a factor of sine. Then it said, according to the table, use the identity, because remember we're here, that sine squared is 1 minus cosine squared. So split off a factor of sine and then use the identity. That means that this is going to be 1 over 6, 0 to 3 pi. In place of sine squared, I'm going to use the identity that is 1 minus cosine squared u times this original cosine squared u times sine u. Then it said do u sub, and this is the second time we would apply u sub. Make substitution that u is cosine x. Well, I'm going to have to do w is cosine u, because that's the final bullet. So w is cosine of u, and dw du is negative sine u. So dw is a negative sine u du. Some of the u's look like my w's. I apologize. So w is cosine u. dw du is negative sine u. Cross multiply dw is negative sine u du. I would need a negative on the inside and the outside before I change over. Also, we'll need new limits because I'm going to w my second round of u sub. Now, the new limits will wait for just a moment. You will have negative 1 over 6, 1 minus w squared times w squared dw. Negative sine u du is my dw. Cosine u quantity squared would be w squared, and 1 minus cosine u quantity squared would be 1 minus w squared. And my new limits, u was 0, so w is the cosine of 0, which is 1. U was 3 pi, so w is the cosine of 3 pi. And if you think about 3 pi on the unit circle, you go from 0 to pi to 2 pi and go another pi, and you're there at 3 pi. Cosine is negative 1 and sine is 0. So my new limits, in place of u equals 0, this is kind of odd now, I put 1. In place of 3 pi, I put negative 1, but we know that doesn't look right. The larger limit's supposed to be on top and the smaller one on the bottom. So to change those and correct it, I multiply my outside by a positive. So a negative, or excuse me, by a negative, which becomes a positive. Flip your limits, and that's 1 minus w squared times w squared dw. So now I get a positive 1 over 6 on the outside, and all is well. My limits are in the order they need to be. I didn't do anything wrong here. In place of this 0, u equals 0, my w is positive 1. In place of this u equals 3 pi, my w is negative 1. But I want to change my limits around by putting a negative on the outside. And then that becomes 1 times w squared is w squared minus w to the 4th. Then we've got to integrate. The good news is this is a definite integral, so we don't have to go all the way back to x. We can just integrate and use our new limits. So when you integrate, the antiderivative of w squared is 1/3 w cubed, and w to the 4th is 1/5 w to the 5th, from negative 1 to 1. You'll substitute in 1 first, and then you'll substitute in negative 1 for the purpose of cutting the lecture short, because I'm going to show you this same problem going through u sub just one time, because it cuts down on the work. I'm going to give you the final answer for this one. The final answer is going to be, if you do this correctly, fundamental theorem of calculus, 2 over 45. And that's basically doing u sub twice, a u and a w. Fundamental theorem of calculus, substitute in 1, minus, substitute in negative 1. So you'll have an answer here, substitute in 1, minus whatever answer you receive when you substitute in a negative 1. You'll actually see that substitution when I show you u substitution once now. So I wrote that out because some of you may need to do it twice to do this same problem. This is me doing it one time, and it saves you a lot of work. So going back to the problem in standard form, again, m is 3 and it's odd, n is 2 and it's even. So I go to the table that says to split off a factor of sine. That's how I got sine of 6x quantity squared times cosine of 6x quantity squared times sine of 6x with respect to x. So this is the factor that I broke off, and I didn't change the problem. Then what I decided to do is go ahead and use the identity that they told me to use. So they said that sine squared x is 1 minus cosine squared x. Therefore, sine of 6x quantity squared also has to be equal to 1 minus cosine of 6x quantity squared. So these two are equal according to the Pythagorean identity, which you could also say that sine squared theta equals 1 minus cosine squared theta. It doesn't matter what x is or theta is, this is always going to be a true statement. So the part that you see here, I split off a factor of sine 6x according to the bullets in the table. So that's over here. Then I use the relevant identity for sine squared or sine of 6x quantity squared. I replaced it with its equivalent, 1 minus cosine of 6x quantity squared. What you see here is me just bringing down the factors of cosine 6x quantity squared and sine of 6x quantity squared. That's all I did, is bring those down with it in the next step. But this is a swap out. Switch it and doing what they tell us to do. Then I go and I do my u sub. So here's my u sub one time. Let me go ahead and just remove that. That's my u sub one time. Instead of letting u be 6x and then w being cosine of u, you can let u be the entire cosine of 6x. Its derivative using the chain rule is the derivative of the outside, which is negative sine, evaluated at the inside, which is 6x, times the derivative of the inside, which is 6. And you can see du is negative 6 sine of 6x dx. Same deal with limits. If x was originally 0 and you substitute that in here, 6 times 0 is 0, cosine of 0 is 1. If x was originally pi over 2, substitute pi over 2. 6 times pi over 2 is 3 pi. Cosine of 3 pi is negative 1. And so in this step, you can see that I have placed, and I think I may have made a small mistake in my work. Inside, let me change that. That should be a negative 6 on the inside and a negative 1 over 6 on the outside. So sorry about that. So I put the negative 6 on the inside, and the negative is reciprocal, negative 1 over 6 on the outside. In place of cosine of 6x, I put u. So here goes from x to u. Negative 1 over 6 is on the outside. In place of my original limit 0, I put 1. In place of my limit pi over 2, I put its equivalent, negative 1. 1 minus cosine of 6x quantity squared is the same as 1 minus u squared, because u is cosine 6x. Cosine of 6x quantity squared is just u squared. And then all of this, negative 6 sine of 6x dx is my du. So I've changed over to u completely, including my limits. Distribute the u squared to both of these, and you get u squared minus u to the fourth. I went ahead from here to here and I put a negative on the outside. A negative times a negative gives me a positive 1 over 6, so that I could change my limits to the order that I'm used to, negative 1 to 1. So I applied my integral properties here to be able to switch those limits. Then the antiderivative of u squared is 1/3 u cubed. The antiderivative of negative u to the fourth is negative 1/5 u to the fifth. And again, you can see I've got to perform the fundamental theorem of calculus. This time you'll see the fundamental theorem of calculus. I'm going to substitute in 1, and then I'm going to substitute in negative 1. Here's the substitution in for 1. And the 1 over 6 is kept outside the entire time. Here's the substitution in for negative 1. So here for 1, I got 1/3 minus 1/5, which is 5/15 minus 3/15, which is going to be 2/15. LCD is 15. When I substituted in negative 1, I got a negative 1/3 plus 1/5. Remember, a negative raised to the 5th power is a negative. A negative and a negative make a positive here. 1/3 times negative 1 cubed is a negative 1/3. I kept it in parentheses because I've got to distribute this negative to both of these or to a single term. I got the single term first. Negative 1/3 is negative 5 over 15 and 1/5 is 3 over 15. So this together is a negative 2 over 15. Then I decided to distribute my negative and I got positive plus 2 over 15. And that gave me 1/6 times 4 over 15. I canceled out common factors here of 2, which gave me a 2 here and a 3 here. So the final answer in my numerator, 1 times 2 is 2, and 3 times 15 is 45. So the final answer is 2 divided by 45 for the problem, which is a lot of work, but U sub once is a lot faster than I said that wrong. I said that correctly. U sub once is faster than having to do U sub twice. So keep that in mind. And as far as the original handout, the answer was D for this one. 2 divided by 45. You can see the other options very close. So if you make one wrong move, limits or whatever, change in limits, then you miss the whole problem. So be very careful. Now the third problem is Roman numeral number 3, powers of tangent and secant. I've got a power of secant here, and it's a cubic power. And then you have your answer choices here. So I'll give you a moment to write that down, and then we'll look at that one. This one is actually pretty simple compared to the one we just did. I wrote down the problem, and then I did U sub on that. I let U be 8x and du is 8dx. So that means I need an 8 on the inside and a 1/8 on the outside. So I did that. And then I changed over to U. So this problem that started in X is now a problem in U. So it's 1/8 antiderivative of secant U cubed du. And this is where I go to my blue box special. My blue box special for secant cubed is on the second page. And it is here. 1/2 secant x tangent x plus 1/2 natural log absolute value of secant x plus tangent x plus c, except I'm going to have to put u's here. If I ask for the formula, cut, paste, glue stick with the x's, even though I'm about to use the formula with u here instead of x. So here we go. The next step that you see is the blue box formula. The 1/8 is on the overall outside here. And I ran out of room. There's my plus c in case you're wondering, Miss Manhart forgot plus c. So 1/8 in brackets is the blue box special from the formula sheet, and then plus c. We've integrated. Once we go to a blue box, we've integrated. So I don't want to see you bring this integral symbol down with you. You no longer bring the integral symbol. You've integrated once you introduce the blue box special or formula for that. So that's why you need a plus c. Now, if you notice, here's the blue box with u and not x. So we will have to go back and remember that u is equal to 8x, and that's my next step. 1/16 secant u, tangent u, distribute the 1/8 plus 1/16 natural log secant u, absolute value of secant u plus tangent u plus c. And then here is me substituting that 8x in for my u. You can see how easy that is. And then that is your final answer. And you can go to your original sheet and you can pick that out. And I do believe it's answer B. So I forgot to box this. There's your check. And here on your sheet, it is answer B. So for this handout, the answers were number 1, D, number 2, D, and number 3, B. Here. So I'll circle those now. D, D and B. If with this video, if you'd like to have a copy of this particular practice test, instead of pausing this and you'd want your own blank copy, I can send that to you through an email. You just have to email me and request to have it. Make sure you say that it's the practice problems that I used in the making of this video. And I'll know that you're referring to this document, and these are the answers that were generated. I call it Lecture Video for Chapter 8, Fall 2017 is what I call the document. So D, D, and B for your final answers there. Now, I still have not represented the entire section. So I do have just a few more examples that will help you see the rest of the section. Namely, I have not covered Roman numerals 4 and 5. Roman numeral number 4 would be products of tangent and secant, and there's a table for it. And then there's alternative methods here as Roman numeral number 5. So this one was 4, and this is 5. So I have basically 2 more examples to show you. The one that I want to talk about first is secant of 2x to the 5th times tangent of 2x cubed. This is another problem where you could do u sub once or u sub twice. I'm going to show you u sub one time. So I've already taken the liberty of writing down all of the steps, but I'm going to rewrite those for the effect of the video. First thing you want to do is notice that it is a problem from Roman numeral number 4, products of tangent and secant, and it's not in standard form, so you need to rewrite it as tangent of 2x cubed times the secant of 2x to the 5th. Now that is standard form, so that you can go to your table. So going to the table, I know that my m is 3 and it's odd, and I know my n is 5 and it's odd. The table says I could either pick out that n is even, which that's not true. N is odd. M is odd, that's true. And then m is even, n is odd. They're both odd, and there's not a case for when they're both odd. So I'm going to go to the situation where I know m is odd. Split off a factor of secant x tangent x. Apply the relevant Pythagorean identity, and then the u sub that you're going to go through is u equals secant x. Again, you could do u sub twice, which is harder, more steps, or u sub just one time. I'm going to show you how to do it the easiest way, u sub one time. But if you have to do u sub twice, then that's okay, as long as you arrive at the answer. Correct answer. Now I want to follow the bullets. It said to split off a factor of secant x tangent x. So it's going to look like this. That's going to become tangent of 2x quantity squared times secant of 2x to the 4th times tangent of 2x that I split off, and then secant of 2x dx. I have not changed the problem by splitting off a factor of tangent. That's still tangent cubed, and this is still secant to the 5th power. Then it said apply the irrelevant identity that tangent squared is the same as secant squared minus 1. The same concept that I talked about earlier. We know from our calculus days that tangent squared theta plus 1 equals secant squared theta. Or you could say tangent squared x plus 1 equals secant squared x. But it's also true that tangent of 2x quantity squared plus 1 is equal to secant of 2x quantity squared. So that's what I'm going to do here, and I'm going to solve this equation for tangent of 2x quantity squared by subtracting 1. That brings me back to my problem. In place of tangent squared, I'm going to do what the table says. I'm going to replace it with secant of 2x quantity squared minus 1. So this is a swap out. They're equivalent. But I have to bring the rest of the information down with me, so I still need to multiply by this secant of 2x to the fourth times the factor of tangent I split off times the factor of secant I split off, and then obviously dx. So the only thing I did from this step to this step is I replaced tangent squared with its equivalent identity, secant squared minus 1. Then it says u sub. If you're going to do u sub once, you need to do the following. And I think that I'll just write the u sub here. Let u be secant of 2x. You may want to do u sub before you distribute. The reason I'm doing u sub once, again, it's easier. If you apply the chain rule, the derivative of the outside, which is secant times tangent. But it's the derivative of the outside evaluated at the inside. So it's the secant of 2x times the tangent of 2x. So derivative of outside, secant times tangent, evaluated at inside, times the derivative of the inside, which is 2. So 2 secant 2x, tangent 2x. And that would be du equals 2 secant 2x tangent 2x dx if you cross multiply. And you get excited because you got, or I do, secant of 2x times, multiplication's commutative, so you can put secant in front of tangent here. So you would need a 2 on the inside and a 1/2 on the outside. So I'm going to box this and then arrow this down. I'm going to put 1/2 on the outside. It's still secant of 2x quantity squared minus 1 in parentheses times secant of 2x to the fourth. And I'm going to go ahead and change and make that 2 times the secant of 2x tangent of 2x. Multiplication's commutative. So originally it was tangent times secant, but I made it secant times tangent so that I can see all of that is my du. So 1/2, and this is going to be u squared minus 1 times u to the fourth du. U is secant of 2x. So it becomes a very simple looking problem. You will have to distribute the u to the fourth power to both of these. When you have like bases and you're multiplying, you add exponents. So please make sure you say that's u to the sixth power minus u to the fourth. Do not say 2 times 4 is 8 and make that exponent 8. 2 plus 4. I think that if you say it's u to the 8th power, you're thinking about this. U squared to the fourth. Exponent raised to an exponent multiply exponents. But when you have u squared times u to the fourth, you add 2 plus 4 and get u to the sixth. So those are two different rules there. And we have this rule. Add the exponents. So then we find the antiderivative. And so we no longer need the integration symbol. That's 1 over 7 u to the 7 minus 1 over 5 u to the 5th plus an overall c. Distribute the 1/2 and you see that you get a 1 over 14 u to the 7th minus 1/10 u to the 5th plus c. Final answer is now ready. U is secant of 2x. So your final answer is going to be 1 over 14 secant of 2x to the 7th power minus 1/10 secant of 2x to the 5th power plus c. U substitution one time. U is secant of 2x. So take a moment to let that sink in. I want to show you what the test question would possibly look like for this problem. This particular problem was actually an old quiz in this particular section. And again, that's your final answer. And I wanted to show you the work for that. And again, that's with u sub 1 time. So there's your final answer, which is much neater than what I just wrote out for you. So the handout with this very same problem looked like this. If you look at the directions, it says 2 methods for the same problem, u sub twice or u sub once. You decide which method, please. Regardless, you get the same answer. Only work one method. I will grade only one. The method of your choice. Method 1, more traditional way, but more work, and that's u sub twice. Go through u sub and let u be 2x if you're going to do u sub twice. U is 2x. Then use a table and make sure that your problem is in standard form before giving m and n. Once you go through the first round of u substitution in the table to simplify the integrand, you will need a second round of u sub, and I let w be secant of u. That's how you would set it up if you wanted to do u sub twice. And I'm going to come back to this page. The second page of this does exactly what I just did for you today on the video, is I went through u substitution once. Again, the thing you want to do is put it in standard form. Pick out the fact that m is 3 and n is 5. Go to your table. Your table said to split off a factor of secant tangent. I split off a factor of secant x, and this became secant to the 4th times secant. I split off a factor of tangent cubed, and it became tangent squared times tangent. I did what the table told me to do. It said in place of tangent squared, put its equivalent Pythagorean identity, secant squared minus 1. And I hope that you see most of the time when they tell you to split off a factor, what you're splitting off, like the Kit Kat bar, break me off a piece of the Kit Kat bar, that piece that you've split off is going to help you with your du, which this is u sub once. If u is secant 2x, du is 2 secant x tangent 2x dx. And then this is the stage where I needed to put a 2 on the inside here. I skipped that step and a 1/2 here before I changed over to u. And then there's your final answer. That's with u sub once, like I just did. Very little work compared to if you do u sub twice, which I have it written down on the worksheet how you do u sub twice, and I can do that now to help anyone that would like to see what it would look like if you do u sub twice. If you don't care about seeing what it would look like if you do u sub twice, then just skip over this part of the video. I went ahead and put it in standard form to show you the beginnings of u sub twice. So tangent of 2x cubed times secant of 2x with respect to x. If you're going to do u sub twice, you're going to start off with u sub instead of going to the table. U is 2x and du is 2 dx. So you put a 2 on the inside and a 1/2 on the outside. Now it's tangent of u cubed times the secant of u to the 5th du. Again, here I put a 2 and a 1/2 on the outside. Du is 2 dx. And I believe I'll put my 2 and my 1/2 to show you in a different color. Again, that's a 2x. I almost wrote 5x. Once you have it in u sub once, this is u sub once, so you'd box it. Then you go to your table, and your table tells you to break off a factor of tangent and secant. This is where you would reveal that that's tangent u squared secant of u to the fourth times a factor of tangent times a factor of secant, which again you could change those two around. Multiplication's commutative, secant u times tangent u. And then it says use the relevant identity. Then in place of tangent squared u, put secant squared u minus 1. Bring down this factor of secant u to the fourth. And I'm going to go ahead and switch these around. The two that I split off, they're going to help me in the future with my second round of u sub. And you're basically ready for your second round of u sub. With your second round, I choose to use w and let it be secant u. So dw du is equal to secant u tangent u. dw is secant of u, tangent of u du. And thankfully, it's already there. We don't even have to put a real number on the inside, and it's reciprocal on the outside. So there's the box for the second round of u sub. That's going to be 1/2 w squared minus 1 times w to the fourth. And then all of that's my dw. You would distribute the w to the fourth and get w to the 6 minus the w to the 4. You would find the antiderivative, 1/7, w to the 7th, minus 1/5, w to the 5th, plus c. And then go all the way back to x. Remember what you said, w was equal